Here we have the Higher 2019 paper. This is paper 2, question number 5. Now this question focuses on the relationship between graphs of functions and graphs of derivatives of functions. What we have to be able to do in this type of question is, if we're given the sketch of the function itself, we have to be able to translate that across, use the information in the diagram and what we know about functions to then be able to draw the graph of the derivative of the function. Now, there's a couple of things you need to make sure you remember, and the key thing for this type of question is that what we're able to do is relate the derivative to the gradient of the line. Remember, derivative means rate of change. When we're looking at a line, the way it changes depends upon the gradient. It tells us the slope of a line. Now, what we have to make sure we remember is there are 3 ways we can have the gradient. We know that we can have the gradient of a line, which is greater than 0, equal to 0, or less than 0. Now, what this means, this has different effects on the behaviour of the derivative. If our gradient is greater than 0, what that then means is that our derivative is greater than 0 as well. So our derivative is positive. So any point here where the derivative is positive, when we sketch the graph of the derivative, it's going to be above the x-axis. It's going to have a positive value. Now, when our gradient is equal to 0, we have a flat line. Now, what that means is that our derivative, g dash of x, is going to be equal to 0. Now, when we work with derivatives, what we do when we do g dash x equal to 0 is we've got to remember we use that to calculate the roots of a function, i.e. the x-intercepts. These are also relating to the stationary points of the original function. So whenever we've got g dash of x equal to 0, i.e. our derivative cuts along the x-axis, this equates across to the roots of the derivative, and this then is what's given by the turning points of the original function. And when a gradient is negative, the implication we get from that is that our derivative, g dash of x, is also negative. So at any point where this is the case, the graph of the derivative is going to be below the x-axis. So it's going to have a negative value. What we have to do is firstly be able to determine which kind of function our derivative is going to take, and then use this information in the properties in the original graph to be able to determine what it looks like. Well, first thing we should look at is the shape. Now we're going to just set out our x and our y-axis here for our derivative, so we know what we're going to be sketching on. First thing to do is determine the shape. Now if we look at this function here, it's a curve that looks something along the lines of that. It's got 2 turning points, gradient changes and then changes back. This is a cubic function. If we've got a cubic function, the highest power is x to the power of 3. Now it could be something like 10x to the power of 3, whatever we want. Some sort of coefficient in front of the x cubed could be fine. The key thing is the cubic. Whenever we take the derivative of a cubic, we end up with a quadratic, i.e. an x squared. And the shape of a quadratic is given by that. Yeah, so quadratics are given by this sort of shape here. So instantly we can look at that and say, right, it's going to have the shape of a quadratic and it's going to be doing this. Now another thing we could tell is that it's going this way, so it's going down the way, as in it's a bowl rather than a cup that's upside down, purely because of the shape of the cubic. If the cubic were coming down, up like that, then this would translate over to a quadratic that's in this sort of shape here. But because our cubic's going this way, we know it's going to be a quadratic that looks like a cup. What we then need to determine is what the behaviour is. We'll firstly look at the stationary points. If we look at this, we've got a stationary point at -2 and a stationary point at 4. For both of those points, those are the equivalent of the roots of our derivative. So what that then means is I know that I can firstly mark on -2 and 4, and I know that those are going to be the roots of my function, i.e. the points where the derivative cuts the x-axis. Now all I need to do is determine the behaviour out with this. Well, if I look at the behaviour below -2, so this section here, the gradient of this line is always going to be positive. Yeah, it's going to change value as the cubit gets closer and closer to the stationary point. However, the value is always going to be positive. That means the value of my derivative is positive, which means that I'm coming down from above the x-axis to there. If I then look between -2 and 4, it's a negative gradient the whole way through. So what that means is my derivative is going to be less than 0 the entire way through. So at this point, it's then going to come around and come up that way like that. And then I know my gradient above 4 is positive. So it's then going to shoot off in that manner there. So what this information has allowed me to do is sketch my derivative, which I know is a quadratic, and mark on the key bits of information, i.e. the roots. Now, I've no other real big bits of information. I can't determine a turning point because I've not been given the function itself. So I can't determine where that lies in terms of y. So we don't have a coordinate for the turning point of our derivative here. But what we've done is we've translated over the relevant information we do have from one sketch to another, and we're able to do it that way. What this then does is this gives me the solution here. Now, there's a couple of points that we can get for this. This question here is worth 2 points specifically. The first point is for the shape of the quadratic. So the first point is for the actual shape of the curve. The second point is for having a turning point here, but it's for having the x location of the turning point. Now, I know I said a second ago we can't have the coordinate, and we can't have a full coordinate for it. But having information like that is something we're able to do. We know the turning point, because it's reflected across it, is going to be midway between the 4 and the -2. So if I do 4 plus the -2, so 4 take away 2, which is 2, and then half that, I know that my turning point is going to occur at 1 in the x direction. The y we cannot mark on. We don't know the value for y. We don't have a given function for it, so we can't determine it. However, we have to make sure, if we can, like in this example, we mark on that key bit of information. I wouldn't get the second mark if I didn't. You have to have the parabola, the correct shape, with as much information as you possibly can marked on it, i.e. the roots and where the turning point occurs in x. If you do that, you'll nail it, you'll get both marks, and you'll walk away by 100% for this question and show you've got a good understanding of how graphs of a function relate to graphs of their derivatives.